Again.
Thank you. So I would like to continue where I left off with quantum walks, and then I will show how quantum walks generalize to quantum singular value transformation and will lead to many algorithms in a succinct way. So back to quantum walks, just definition again, just to recap. We had a graph with weighted edges with non-negative weights, and we had the Laplacian, which was edge weights, and the diagonal corresponding to the negative sum of all the edge weights, so that columns and rows sum up to 0. And we had continuous time quantum walks, but now I want to talk about discrete time quantum walks. And well, for this, first study the discrete time Markov chain, the discrete time random walk, and the transition probability matrix of this walk, which this matrix P is such that the element VU describes the probability of stepping to V once we are at vertex U. And this probability is just corresponds to the weights, so we just need to take the edge weight corresponding to this edge and normalize with all the other edges adjacent to U. This is how you define a discrete time version of the random walk. And in a quantum walk, we will have a unitary version of this walk operator. So what is one step of the quantum walk? We are at state U, and we want to step to state V with the probability PUV. So if we have unitary, which from state U prepares state U and V with these amplitudes, if I would measure this state after one step, then the first register would contain the next element. If I would somehow get rid of this U and just do one more step, measure, then do the step measure, I just get back the classical random walk. So this unitary certainly enables me to implement the classical random walk, but it will enable me to do more. And so here is a question. Remember, I told you that if you could prepare uniform superposition over permutations or lattices, then you can do very powerful things. And there, the problem is that you sort of need to erase the history of your procedure that prepared this distribution, because uniform distribution over all permutations of a graph is very easy to prepare classically in a stochastic manner. Also, Gaussian distribution on a lattice, you can also do it efficiently. But somehow these classical methods will somehow have a history. They kind of have a particular ways of getting at a point, and erasing the history is very difficult in general. That's why these algorithms don't go through. But in this quantum walk setting, there is a way to somehow get rid of this history, which prevents you doing efficient things in the error settings. So how do you do that? Well, the trick is just apply this unitary update operator in a clever way. So first you apply the unitary update, then you swap the two registers, and then you act with the inverse of this update operator. And well, for technical reasons, it turns out to be very useful to also add the reflection operator. So this operator, what does it do? It says that if the first register is in the 0 state, then don't do anything. And if the first register is other than 0, then flip the sign at the minus phase. This is somehow very useful to have. So this is like an intuitive walk operator, and we need to add this small modification to work it nicely in a quantum setting. And all what I tell you is actually generalizes to weighted graphs, as I told you, but for simplicity now I will assume that you have a symmetric Markov chain or a symmetric walk, which means that all the edge weights, all the weights in a row or a column of the matrix are the same, so the total edge weights adjacent to any vertex are the same. And this is an easier setting to analyze, but everything generalizes. So in this case, in particular, I have a symmetric chain, so the transition from U to V has the same probability as from V to U. Yes, and now in this setting, we can intuitively understand why this walk operator that I defined is useful. Well, what turns out that the top left corner of this walk operator is just the transition matrix. So it directly corresponds to the classical random walk. And here is a quick proof. So how can I show that the top left corner is just P? Well, let's take a look at the UV matrix element of the top left corner. Let's just describe this way. So what is that? I expand this W prime operator, write down the definition, and then now I group these states. It's like it's one step of the quantum walk here, which is the superposition over U primes attached to V, and this is just the adjoint of one step. So here is one step of the quantum walk, which is V primes adjacent to U, but now we need to take the adjoint, and there is a swap between. So what's this inner product? Here I have a U, and here I have a V, so these orthogonal bases. So it means that the only non-zero term, cross term here will be U equals U prime. So here, the swap means that this U needs to be swapped to the first, and this V will swap to the first register, so V equals V prime. So the only non-zero term in this product is the UV term, and you have like square root PVU, square root PUV, that is just PUV because we had this symmetric setting. So really you can see that the top left corner of this walk operator is just the transition matrix itself. That's a very nice connection. And here I should mention that this reflection operator that I added, this just adds a phase to things starting with a 0, but in the top left corner everything starts with a 0, so it doesn't change anything. The top left corner of this modified walk operator, this W, is still just P, doesn't change by this addition here. All right, so now let's do multiple steps with this quantum walk operator, and let's see what happens. And well, I tell you that some Chebyshev polynomials will appear. K step of the quantum walk, the top left corner after k steps of the quantum walk will be just a Chebyshev polynomial, the k Chebyshev polynomial applied to the transition matrix P. If you are coming from classical background, it doesn't make much sense probably, like why would you take a Chebyshev polynomial of a stochastic matrix? Well, this is what happens quantumly, and it will make sense in a bit. So here I don't want to provide too much proofs in this talk, but this is just one succinct proof that I want to show you. So the Chebyshev polynomial is just defined as the cosine of k times the arc cosine of x, and it's really a polynomial, and it has a very nice recurrence relation that the k plus 1 Chebyshev polynomial is 2x times the kth minus the k minus 1th Chebyshev polynomial, and I will use this in the proof. So let's start. The 0th Chebyshev polynomial is just 1, constant 1, so if you apply to it matrix, it's just the constant identity. And indeed, if I don't do any quantum walk step, then the top left corner of the identity matrix, the no quantum walk step is just identity, so the 0 case is done. Well, what's one step of the quantum walk? I have just W here, and I already showed you that the top left corner of W prime is just P, so I have also the case for k equals 1, and now I can use the recurrence relation. So I show the induction step. Now let's take a look at the k plus 1 step of the quantum walk and the top left corner of that. Well, I just separate the last walk operation, which is W prime times the reflection, and I did the k step as before. I just expanded, and now I will just expand this sum along this reflection operator. So first I have this projection here, and that gives rise to W primes times 2 times this projection WK. And here I do a funny thing, like this is a rank 1 matrix, 0 tensor 0, and I can just separate it this way. It's just a matrix multiplication. But if I look at this part, the second part, it is just exactly the k step of the quantum walk, so it's the k-Chebyshev polynomial as by induction. And if I kind of wrote it a bit cheating way, but if you take this projector out on the left-hand side, you have w prime and the top left corner of that with a factor 2, so it will be just 2 times p. So this first term is 2p times take kp, and what's the minus? With the minus, I have an identity here, the w prime and the w here, but w prime was self-inverse. So from this definition, it's very easy to see that w prime is self-inverse. So when I have this identity sandwiched, then it's just will reduce the exponent of the w thing here, and I have tk minus 1. So this shows my induction that indeed, if I had the Chebyshev polynomials up to k, then it is also up to k plus 1, and it's true. So it may be a bit counterintuitive, but quantum walks just perform a Chebyshev polynomial transformation on the Markov chain matrix, and this turns out to lead to quadratic speedups in quantum walk algorithms. And to understand intuitively why you have quadratic speedup, I will formulate this fast-forwarding version of Markov chains. And for that, I need to introduce a very nice trick, which is used in Hamiltonian simulation a lot, which is linear combination of unitary matrices. So here, suppose that I can do like a controlled evolution of the U. So if I have, it is like in phase estimation, if the ancilla qubits are describing an integer k, then apply the kth power of unitary on the second register. This is one ingredient I need, and I need a state preparation unitary which prepares a superposition of ancilla states with some qi coefficients square rooted, so that it's this is a probability distribution. So suppose that I have these two unitaries, that I claim that the following circuit, so take the top left corner of this QVQ circuit, then the top left corner I insert zeros, maybe the following. So this is just the circuit, prepares the state, superposition of states, applies the power of unitary, and then unprepares the state. And if I start with zeros and measure zeros, then this corresponds to the top left corner of the unitary matrix. And it just turns out to be that this powers of this unitary with the weights according to this probability distribution that was in my state preparation problem. So this is how linear combination of unitaries work. It's really simple math to work out the proof of this statement. And if my U matrix was just a quantum walk operator W, then I know that the top left corner of W was just the k-Chebyshev polynomial, so the top left corner of this huge matrix will be just the linear combination of Chebyshev polynomials. And a nice corollary is that we can implement a unitary operation, a quantum walk operation, at the top left corner up to epsilon precision is just t steps of the original Markov chain. And the nice thing here is that I only use about square root t times the quantum walk operator. And the proof of this is that I want to implement the polynomial x to the t applied to the transition matrix P, but this monomial x to the t can be very well approximated by a small linear combination, a small convex combination of Chebyshev polynomials. And so these Chebyshev polynomials only go up to square root t, and then I just apply this linear combination of unitaries lemma, and now I implemented t steps of a Markov chain with only square root t quantum walk operations. And this explains why you have quadratic speedups in a quantum walk setting. And in particular, we get the following results. So we can get, suppose that we have some unknown mark vertices M, then we want to find a mark vertex. And classically, we can define the hitting time, which is the expected time to hit a mark vertex when we start from the stationary distribution. And if we can prepare a superposition corresponding to the stationary distribution, which in the previous case, by the way, when we had a symmetric matrix, was just a uniform distribution, so it's very simple to prepare. Then Szegedy showed how to detect the presence of marked vertices, so that see that M is not empty in time, which is quadratically faster than classically, quadratically faster than heating time. It's a result from 2004, and this was later extended to a version where you can also find marked vertices, but in a slightly different quantity, which is an upper bound on the heating time, which is the spectral gap of the quantum of the random walk, and so that's delta, and epsilon is the ratio, is the probability that an element in the stationary distribution is marked. So it's like initial success probability. And if you take and if you take 1 over that many steps, classically it's an upper bound on the heating time, and in the square root of that you can actually find a marked vertex. But it was unknown for a long time how to actually find a marked vertex, not only detect the presence of marked vertices in the square root of the heating time, and we could recently solve this problem by Andris, Stacy, Martins. And so this problem was open for a long time, and the reason why we could make progress here is that we looked at Markov chains using this fast forwarding method. And this really gives a much insight how this quadratic speedup happens. People previously analyzed these quantum walks very differently. They were thinking about the quantum walks as a walk on the edges of the graph. And that tells you something, but here it's more direct connection to the classical process, which is useful. And so you might wonder, okay, why do you always want to start from a stationary distribution? It may be hard to prepare, or it's maybe not the best ansatz for finding something. So actually there is a version where you start from an arbitrary distribution sigma, and then Bellows showed how you can detect marked vertices in the square root of the commute time between the marked vertices and your initial distribution. If you start from a single vertex, then the commute time is just the expected time from your vertex to reach a marked vertex and going back. Or so, in some cases when a sigma or m is like singleton, it has an easy combinatory interpretation of this quantity, but it generalizes to more general setting, and it's defined via electric network quantities, so effective resistances and so on. And we show that in general, you can find a marked vertex, not only detect the presence in the square root of this commute time, and so we worked with Simon and Stacy on this problem and recently finished the result. This also goes through this framework, but interestingly, in the same time, Stephen Piddock from Bristol, he could also find a way to also find marked vertices, but he used the original formalism. So somehow it seems that two very different techniques converge to the same result at the same time. It's very, very surprising. We just figured out that we had the same result. So I don't know why it happens that so many times you just find the same result even through very different approaches. It's intriguing to me always. Maybe it's just a reason. Maybe it's just the result of much funding in quantum, but maybe it has more interesting reasons as well. Okay, and I will not go into details, but I just tell you some major applications of quantum walks. So it turns out that quantum walks on Johnson graphs are extremely useful, and the Johnson graph is a graph on subsets of a base set. So N is my base set, and I have subsets S of a fixed size, and I define edges that these are sets which differ in one element. So the symmetric difference is 2. These are the subsets that are connected, and this Johnson graph has nice properties. It's symmetric. You have uniform superposition as initial distribution, so everything is very nice. And you can apply it to element distinctness. You can find solve the element distinctness problem quicker and optimally, as shown by Andris and Bainis. And by the way, this algorithm was the was the original motivation of this discrete time Szegedy type quantum walks. And you can find triangles quicker, although the most up-to-date or like the cutting-edge result actually doesn't use quantum walks today by Legol, but you can get competitive algorithms. This way you can verify matrix products, and there really are many applications. If you want to learn more about these applications, Miklos Sánta has a very nice survey paper on this. Okay, so this was quantum walks, and now I want to show you how this generalizes to the quantum single value transformation. And before that, I just want to stress you that it's very useful to look at top left corner of matrices. Somehow it turns out to be the right way to approach linear algebra questions. You have a big quantum circuit. The quantum circuit is a unitary matrix, but in linear algebra you often don't want to work with unitary matrices. So what can you do? You can just look at the top left corner, and that can be arbitrary matrix which is norm at most 1. So let's look at this way. I have unitary, the top left corner is A as I promised you, and the top left corner maybe corresponds to bit strings that start with A zeros or B zeros on one side. So it really just means that start with a quantum state where the first B qubits are 0, and like post-select or condition on seeing a quantum state which the first A qubits are 0, and this defines a rectangular top left corner here. And so this is a nice way, unifying way of thinking about algorithms, because many known input models can efficiently, you can use many input models to efficiently construct block encodings. This is what I call block encoding of matrices. So for example, if you have an efficiently implementable unitary, then the top left corner is just, the whole matrix is a top left corner, so you can implement a block encoding. That's not a surprise. What is more interesting, that if you have a sparse matrix where you can efficiently compute the location and the value of these non-zero elements, then you can also quickly implement block encoding of the matrix divided by sparsity. But more recent algorithms focused on some machine learning applications where you maybe have some big database stored in a quantum realm. Turns out matrices stored in a quantum realm in a clever data structure can be also put as a block encoding efficiently. But you can think about more physics related representations. Suppose that you have density operator rho, and you can implement a purification of a density operator. So to say, you can prepare this quantum state on a quantum computer, then you can also put as a top left corner of a unitary matrix as a block encoding. And it's really quite general. Like, you can just think entirely about physics and think about the POVM operator, which is a generalized measurement operator. If you can perform the measurement on a quantum computer, meaning that you can sample from a binary variable proportional to trace rho m, then this measurement procedure translates immediately to a block encoding. If you just look at this measurement procedure at a slightly different angle, the same circuit is a block encoding of the measurement operator m. So it's a really rich way. You can combine matrices which are constructed very different way. Maybe you have a matrix which has a sparse component, and then which you can efficiently compute and then deal with that. And maybe it has a non-sparse component, but which has some other nice property. It comes from some POVM or has some other handle you have on it. Then you can combine these and then then do a lot of things that I will show you. First of all, what I showed you already, how you can implement convex combinations of operators. So you have block encodings. I showed you how you can take convex combinations. Well, I showed you it for powers of unitary, but it works in general. And if you have a matrix with block encodings of A and B, then you can just take the two unitaries, multiply them together, and the new matrix will have A times B in the top left corner. Well, maybe something else as well that you don't want, but you can always just add a few little additional operations that prevent additional terms to come in the top left corner, and it gives you the efficient way to get a block encoding of A times B. Why is it interesting to represent matrices this way? because A and B here can have exponentially big size. And so what you did, you basically we showed how to multiply two exponentially large matrices in a single step. So the quantum matrix multiplication exponent is 0. Okay, well, it's of course not true because you only have a unitary matrix, so it's a much restricted access to matrices, but quantum computers can really efficiently add together and multiply huge matrices. And okay, so I have this very simple framework, but let's push it one step forward. And yeah, okay, sorry. Before I go to the singular transformation, I wanted to just give you an idea how to implement a block encoding of a sparse matrix. So suppose that A is an S-sparse matrix and all matrix elements are at most 1, which are non-zero. And we need sparse access, meaning that we can efficiently find the non-zero elements and then prepare row states. So if I can find the non-zero element locations and their magnitude, then I can implement a unitary which prepares row states, given index I, prepare a superposition of matrix elements in this way, and maybe this is a state of norm at most 1, so it may not be normalized. Then I need to add some garbage to just make it a quantum state of norm 1. But this is easy to implement, and we also need a procedure to somehow implement column state. So given the column index j, prepare a state corresponding to the jth column. And it turns out that if you just put these two matrices together, it's a very simple calculation. I don't want to go into details, but it just similarly as in the quantum box setting, only the I and j element will have a non-zero overlap, and then you will get the ij element divided by s. So it's really a block encoding of the sparse matrix divided by the sparsity. So that's why it's important that you have a sparse matrix. If this matrix wouldn't be sparse and S may be exponentially big, then you have just a very tiny fraction of the matrix encoded. And you can think about it as a probabilistic implementation. So if S is like arbitrarily small, like S is arbitrarily large, then it's almost like a PP algorithm. Like it maybe implements the matrix that you want, but with so tiny probability that you barely can distinguish it from nothing. So that's why it's important to have sparse matrices. All right, and now I want to turn this result, which we had with Yuan Su, Guanghao Lu, and Nathan Wiebe. and this is really a follow-up work on Ike's and Theodore Euler's nice results. So now I state the most general version. It says that if you have a polynomial function which maps -1, 1 to -1, 1, and it's a degree D odd polynomial map, and I have a block encoding of the matrix A, where A can be written without loss of generality in a singular value decomposition form. So these are the singular values, singular vectors. Then I can construct a new unitary, which I denote by U phi, and it's a simple unitary which now has not A in the top left corner, but A with the singular values transformed, but the singular vectors remain the same. So this you can achieve, and this phi is a sequence of angles, of D angles, which is efficiently computable given the polynomial P. And this U phi quantum circuit is just the following. So there is no approximations, nothing hidden. This is the quantum circuit. You have the original quantum circuit U, which had the block encoding had some A and Scylla qubits. Well, in this slide, for simplicity, I assume that A and B, the two side block encodings, are the same size, but it works in more general. So you start with the unitary U, you apply some Toffoli gates, and then you apply a single phase rotation on the Ancilla qubit. Then you apply Toffoli, now you apply U dagger. Again, Toffoli, next phase Toffoli, U, and you implement this for a length of for a D length sequence. And well, you add the Hadamard gate because all successful quantum algorithms should have a Hadamard gate somewhere. And now this algorithm actually satisfies this property. So the top left corner will be this polynomial transformation applied to this matrix. And let's take a look at the condition. So it says that the polynomial must map -1 to -1, 1. Well, it's an odd polynomial, so I might as well just say that 0, 1 to 0, 1. It's certainly necessary because A is a block of a unitary matrix, so the norm is at most 1. Every single values are between 0 and 1. And I want to get a new unitary matrix where P of sigma is a new single value. But again, it's a block of a unitary matrix, so it must be below 1. So any polynomial which I can implement must have this property. And this even this odd constraint is also very natural, so it's basically as good as you can hope for, and basically as efficient as you can hope for. And works completely generally. And one interesting feature here that you should note, that these angles do not depend on the unitary u. Any unitary that you plug in will work, just will transform the top left corner accordingly. And a similar result holds for even polynomials as well. It's a bit more cumbersome to state, so we will not need this directly, so I don't state it. Okay, and I want to tell you a little bit about the story of this theorem, how people got to this. And this whole thing started with the quest of fixed point amplitude amplification. So what's amplitude amplification? You are given a unitary which corresponds to some quantum algorithm, and on a fixed input state you prepare a good state marked with a 0 and the bad state marked with a 1. So the probability of success is like P, because you need to square this, and your goal is to prepare psi good. So it's a story about the good, the bad, and the unitary. And then what you want really is just prepare the good state. So let's take a look at this problem with these new glasses that we just have. What is the top left corner of this matrix? So I start with the fixed state, and I care about the success flag. Well, that is just the first half of the first column of this matrix, which is that just psi good attached with a 0. And so this rank 1 matrix have one singular value, and this is square root of P. So I want to change this square root of P to 1. Now it means that on input 1, my unitary will prepare the psi good state with certainty. Well, maybe I cannot guarantee you that, but I can guarantee that it will be extremely close, exponentially close to 1. So really, here just apply a polynomial which maps everything above square root P to 1. And this resolves a problem that in ordinary amplitude amplification, you can overshoot. So if you don't exactly know what's your success probability, you only know a lower bound, then you apply this Grover search operator, and you might end up with some very tiny success probability, and it's annoying to deal with. And this was the quest in fixed point amplitude amplification, to overcome this difficulty and have an algorithm which works only given a promise on the lower bound on the success probability. And now apply single value transformation with a polynomial which is just like a threshold polynomial. So the polynomial that you have should be just something like this. You have here square root of P, and the polynomial is an odd polynomial, so it must start from 0 but reach roughly 1. Then, if no matter what was your success probability here, you will always succeed with probability very close to 1. And so people tried to solve this problem initially, and the idea was to use Grover search, but in Grover search you have reflection operators and just add a different phase all the time. So this this proposal was there for like, I don't know, 10, 15 years, but people just had no idea how to analyze that. And that's when Ike, Guangzhou, and Theodore Yoder came, and they figured out a way to analyze this, and their result, their insights led to these general results at the end, and much more in Hamiltonian simulation. Okay, so now we have the fixed point amplitude amplification, but we actually have a more general version of it, which we can call singular vector transformation. So here we are given unitary U. Top left corner is a matrix A with some singular values and singular vectors. And so our goal is to transform one copy of a quantum state, which is a superposition of right singular vectors, to the corresponding superposition of left singular vectors. And we have the promise that all singular values all singular vectors that are in this superposition have singular value at least delta. Then we can implement this transformation epsilon approximately using this threshold polynomial that I showed you, and the complexity is just 1 over the threshold times log 1 over epsilon. So this is called oblivious amplitude amplification because somehow it works in a whole subspace and transform singular vectors from one space to another. And it's used in a Hamiltonian simulation and other places. Okay. So another application that I wanted to show you is related to machine learning and regression. So here we are given a matrix A, which is which again has some singular decomposition, and we wanted to implement the inverse or the pseudo inverse of the matrix, which is just a generalized inverse. You need to reverse the order of the singular vectors and invert the singular values, while if the singular value is 0, then just replace it with 0, then you can't do anything. This is called the pseudo inverse. And if the matrix is invertible, this is just the ordinary inverse of the matrix. and here the observation is that if you had A as the top left corner of unitary, then just take A dagger, which is now reversing the singular values, and that's just the top left corner of U dagger, the reverse of the quantum circuit. So if you have A as a block encoding, then you have A dagger as well. And now you just need to apply singular value transformation to A dagger and map these singular vectors, singular values, sigma I to 1 over sigma I. So we wanted to implement this function. So this function is really ugly. It has some problems around 0, and it's definitely not bounded. However, if we have the promise that our singular values are not too small, all non-zero singular values are excluded in this region, which means that the matrix has some bound on the condition number, then we can just find a polynomial approximation which approximates this 1 over x function on this domain where all the singular values lie. So outside this red region, this polynomial, which is in yellow, approximates my function well, and in this small region there is no single value by promise, so I don't care about the approximation there. And this leads to indeed implementation of the pseudo inverse. And so if we have the promise that the pseudo inverse is bounded by kappa, it's a bounded condition number, then we can apply the quantum singular value transformation and implement the block encoding of a scaled down version of the pseudo inverse. And it has polynomial cost in terms of the condition number. And if we want to prepare the quantum state, which corresponds to the solution of a linear equation, then we just need to apply the pseudo inverse matrix to this quantum state, and we might need to apply some amplitude amplification as well on top, but then we will get a quick algorithm for matrix inversion as long as the condition number is not too big, and we can block encode matrices. For example, if the matrix is sparse, we can block encode the matrix. And yeah, this approach can be improved using something called variable time amplitude amplification, and we have other variants possible corresponding to like regression problems where we have weighted least squares or generalized least squares. These are explored and easy to express in this formalism. Okay, and now let's move back to the Hermitian case, which was the originally studied for Hamiltonian simulation. In that case, for a Hermitian matrix, the singular values and the eigenvalues are the same, at least up to a sign, a plus minus sign, and then we don't have that much distinction between the even and odd polynomials. So we get that any polynomial map which is bounded degree d and either even or odd, and we have a Hermitian matrix, then we can implement a polynomial transformation of H. And for example, if my Hermitian matrix was just the symmetric Markov chain matrix, then it would be just applying this approximate polynomial to x to the t. And since we can take linear combinations of matrices, we just can take a linear combination of even and odd single value transformations, so we can get arbitrary polynomials. We lose a little bit with the range, but now we have any polynomial mapping -1, 1 to -12, half degree d. Then we can get a block encoding of a polynomial transformation of the Hermitian matrix H. And we only need to use the block encodings d times and 1 ancilla qubit, maybe a few additional 2-qubit gates. And this is the result which leads to optimal Hamiltonian simulation. So if actually is a physical Hamiltonian which I have as a block encoding, then, well, I only need to find a polynomial approximation of this e to the itx function, and it turns out, as Aiken Guanghao showed, you can find a polynomial which has only this degree, like t plus log 1 over epsilon. I'm hiding some small factors here. So with this complexity, you can simulate this Hamiltonian for time t. And this really achieves the optimal complexity. And maybe you need to use a few gates if you have more ancilla qubits for the block encoding, but it's usually not a big cost. Yes, and the proof sketch is just you approximate the sine and the cosine function, put together, and you solve the problem. So okay, now it's one slide, but it was like 20 years of research. So maybe I should stop here for a few seconds, because it's like 20 years of research in this slide. All right. So what else you can do? Well, we already showed how to put like e to the itx. What about like imaginary time evolution, as physicists would say? So just like put e to the tx in the exponent. Well, that's called Gibbs sampling. So if we have a block encoding of h, the goal would be to prepare a quantum state which is proportional to e to the minus beta h. And this is this idea was already explored by Pauling and Watzian in 2009. And the idea is that you start with a maximally mixed state, which is just the identity subnormalized, and apply the map e to the minus beta h over 2. And then you can see that the new state, when you need to apply this unitary in two sides as its density operator now, it will be just proportional to the Gibbs state that you wanted. And then finally, you need to apply amplitude amplification. But here you need to be careful, because maybe if you subnormalize your state too much, maybe you need to like take an exponential time to amplify this state. So you need to be a little bit careful. So the final algorithm uses minimum finding, where you can find the minimum of a function with a square root number of evaluations. And we extended this to a more general setting of these Hamiltonians. Then we first find an approximation of the ground state energy, H0. And then we use the previous process, but with the map which is truncated at H0. And the final, and the good thing about it is that if we have some overlap with the ground state, and the ground state will not get subnormalized because we shifted the function. So at least we have like 1 over square root n overlap with the final state that we wanted to prepare. So the final complexity of this algorithm in the worst case is beta times square root n. This is just another application of these single value transformation techniques. And with this, I just would like to kind of give you a guide. What kind of algorithms and applications can you get by single value transformation? And I just grouped different aspects of the speedups in different examples and contexts. So you can get exponential speedups using this single value transformation by the dimensionality of the Hilbert space. And this is, for example, in the Hamiltonian simulation application, it's apparent. Compared to previous quantum algorithms, you can get exponential speedups in terms of the precision, which comes from very good polynomial approximations and the fact that you don't need to use the phase estimation algorithm. And this gives rise to, for example, the improved matrix inversion algorithm, which has logarithmic dependence on the precision. And you can also get different type of speedups, which are quadratic. For example, by observing that single values are somehow square roots of the probabilities. This is just the Grover search and amplitude amplification that I showed you. Also, single values are easier to distinguish than probabilities, and this gives you better estimation of probabilities or amplitudes. This is the amplitude estimation technique. And there is a somewhat harder to explain in intuitive terms, but somehow close to one singular values are more flexible. They are somehow, Chebyshev polynomials go crazy around one. So there you can somehow be more efficient, and this is somehow the reason why quantum laws get this quadratic speedup and other results. So this is just a guide, like what type of speedups you can get using these techniques. And a few more applications that I didn't have time to. You can derive, in simple terms, the fast QMA amplification and a fast quantum or lemma, or you can get more quantum machine learning results, principal component analysis, principal component regression, and all sorts of algorithms which deal with single values of large data. You can also implement some version of non-commutative measurement operators, which are used in these state preparation techniques that I told you in the last talk. You can implement fractional queries and much more. So really, it's a versatile tool, and I hope that you will find many more applications. Yes, please?
So given what's going to be talked about this afternoon, which is on the inspired classical algorithm, can you state more precisely what you mean by exponential speedup with respect to the dimensionality of the Hilbert space?
Yeah, I have a slide on that a little bit later. I will talk about this. Yes?
For your last slide, the Gibbs sampling, you have apply map and then e to the minus beta h over 2. That's not in general unitary. How do you apply that on a quantum computer?
Yeah. So maybe I glossed over this a little bit fast. So we only care about the top left corner of the matrix, which means that we only care about states where the first ancillary qubits are all set to 0. So what I mean by that only look at the part of the quantum state where maybe like measure the first ancillary qubits, and if they are all 0, then you have that state. But somehow this is just a succinct way to like tell you the post-measurement state and the probability in the same line. So if you care about the part of the quantum state which has all zeros in the first A qubits, then it will be proportional to that. So the measurement probabilities are also proportional. It's just like looking at one part of the quantum state. Yeah, post-select or amplify, whatever works for you. Indeed. All right. And here I just want to briefly sketch a few results about optimization, and these often build on this framework or like maybe some easier versions of Grover search. But just I wanted to give you a landscape of recent algorithms for optimization based on these techniques. So in general optimization, we want to find the best solution of some function, some minimalization of a functional domain. And if it's an unstructured problem, we have no clue about how the solutions look like or like the function looks like, then this can be solved, this problem, with the square root of the domain size by the Dürr-Hoyer algorithm, which is this minimum finding that I already mentioned. And there are other discrete structures where you can speed up optimization. For example, you can find shortest paths in a graph, and the classical algorithm by Dijkstra runs in n square time. But quantumly, using Grover search and then quantum walk techniques, you can speed this up and get n to the 3 over 2 algorithm by shown by Dürr, Hellingman, Hoyer, and Minala. And you can also get polynomial speedups for match and flow problems, and these are typically based on Grover search. But you can more recent lines of inquiry show that you can also speed up NP-hard problems. The Schöning's algorithm is a very simple example where you can speed up solving the three-step algorithm. It's just a basic implementation, a basic application of the amplitude amplification algorithm. And you can also speed up backtracking, and you can get also polynomial speedups for dynamical programming for either NP-hard problems like the traveling salesman problem that is required to get into PRL. Okay. Now let's turn to continuous optimization. This is where we had maybe more new results in the past years, because we didn't have much result before, so it was easy to be the state of the art. Well, it was not easy actually, that's why people didn't have any ideas, but finally Brandau and Swor, Krista Swor showed in 2016 how you can get a handle on SDPs and get quadratic speedups. And really a line of research by them and some co-authors and with our group at CWI with Joran van Apeldoorn and Sander Gribling, Ronald de Wolf. And also people from Maryland joined this effort. So we had a series of like 4 papers, and we ended up at this complexity of SDP solving, which is the state of the art now. Just to give you context, before applying all these linear algebra techniques, the first result was square root n times square root m, sparsity squared, gamma to the 32. And that gamma is some relative precision parameter. So think about it as like 1 over epsilon reverse. And so this algorithm was improved a lot by using all these linear algebra techniques, and this is how we stand now. And we also showed with Joran how you can get improvements for zero-sum games to find a Nash equilibrium. And you have a similar cost structure, but here this epsilon factor is actually epsilon. It's not a relative precision, and that matters a lot in practice. So this is really just a simplified version of the SDP and fine-tuned so that you have better complexity. And I will talk about this briefly. There is a work on quantum interpolation methods, and recently there was a result on polynomial speedups for estimating volumes of convex bodies, which is based on quantum walks and other applications. And one nice, intriguing application that you can derive using this SDP solver algorithm is the shadow tomography result of Scott Aronson, where you have the following problem. You have an n-dimensional quantum state rho, and we know that if it's an n-dimensional state, then doing tomography has exponential cost. So you want to avoid that. But if you only have a set of m measurements, and you want to estimate all these measurement operators, their expectation value up to additive precision error, then how many copies of the state you need? And Aronson showed this surprising result that you can do much better than like n. So much better than this exponential large Hilbert space. You can do with logarithmic cost, and well, you need to pay polynomial price on the number of on the precision, but only a logarithmic price in terms of the number of operators that you want to estimate. And this result can also be derived using the SDP framework. Okay, and this SDP algorithm is based on Gibbs sampling and an iterative structure, and I show you the zero-sum game version here because it's easier to describe. But the same ideas and the same structure works, it's just more quantum in the SDP case. So in this problem, we have a payoff matrix A, and the expected, and the 2 players, Alice and Bob, and the expected payoff for some strategies X and Y is just X transpose AY. So this is like a probability distribution over plays, and X is like a probability distribution, which is the strategy of Alice, and Y is the strategy of Bob. And if you want to find an approximate Nash equilibrium, then Grigoriadis and Kachian showed in '95 how to do it in a simple iterative algorithm. And it's just the following. You start with some strategies. Well, these are not really strategies, these are like some pre-strategies with 0. And you do the following. For 1 over epsilon square steps, you will update your probability distributions, and these distributions will be like Gibbs samples which will be linear combinations of the rows of the matrix on one side, Alice's strategy, and Bob's strategy will be Gibbs sample corresponding to linear combination of columns. And in each step, you just sample from the Gibbs state on both Alice's and Bob's side. And if you sample the sample A and B according to the Gibbs distribution, you just like update your exponents. You add the tiny amount of this new coordinate to your vector, and now in the next step you will Gibbs sample with the new vectors. You just do it iteratively, and this will finally find an approximate Nash equilibrium where your Gibbs state will be a good approximation of the Nash equilibrium states. And one can view this as a form of a gradient descent or multiplicative weights, and this generalizes to SDPs. Here all these matrix exponents were actually just diagonal matrices. It was very simple. In the SDP case, it's more quantum. You have non-diagonal matrices, and then it becomes like a fundamentally quantum algorithm. But still, you can get interesting speedups in this regime. And you can reduce LP solving also to zero-sum games, so it gives you a fast LP solver in some cases as well. Yes. Okay. And well, I don't have much time left, so I just wanted to have a very brief overview what other results are possible along these lines of ideas, or like in a broad sense. You can get quadratic speedups for Monte Carlo sampling. You can get good estimates in variance over precision time, whereas classically you would need to square this quantity. You can also test properties of distributions with small query complexity. You can test equality to unknown distributions in square root of the domain size, to known distributions cube root of the domain size. You can estimate Shannon and von Neumann entropies of distributions for classical distributions with square root domain size, and for density operators for quantum distributions with linear size of the dimension, but this is actually again quadratically smaller than the size of the density operator, which is n squared. So you get speedups here as well. And the last thing, which I promised you this application to machine learning, and this will be really geared towards Evan's talk. I just want to show you this is one of the most interesting quantum machine learning algorithms, which solves this recommendation system problem, the Netflix challenge. Here you are given a bunch of users, and these users have preferences of movies. They can rate the movies. They may be like a movie very much or not so much or kind of in the middle, but you don't know everything. Like you have blank spots, and you want to maybe recommend a movie to Tom Hanks, and the question is whether you want to recommend Inside Out or The Terminator to him. So how can you decide this problem? So here Netflix obviously wants to solve this because Netflix wants you to be hooked on your screen, so it's really important to give good recommendations. And then the simplistic model behind is that every movie is some linear combination of a small number of features, like drama, comedy, how masculine or feminine is it, and the user taste is also a linear weighing of these features. So this is a simplistic view of like how humans work, but on a approximate scheme it seems to work out. And so this is how you try to find the unknown recommendations. And okay, so the solution here will be just use a principal component analysis. You will find the largest single values of the matrix, and that will help you to decompose movies to features and help to decompose people into weights. So this is the main idea. And how you will get exponential speed up here, that was the question. Well, if you need to put all this outside data to your quantum computer, then you cannot get exponential speed up because you need to touch all piece of data at some point. So in that sense, it's not possible. What you ultimately want to do is prepare a quantum state which is somehow proportional to a vector in your database. Or if you have this matrix, this whole user recommendation matrix, you want to maybe prepare a block encoding of your matrix. So how can you do it with some exponential advantage? maybe at least in an amortized setting. And here we need to consider, here we consider the Netflix case when users in an online manner like movies as they come. There are new users added, there are new movies added, then they watch new movies, they start liking it. And I will maintain a big data structure where the data structure stores these data super efficiently, and then I can exponentially quickly prepare the quantum states. And every time a new user arrives or a new movie is being watched and reviewed, then you only need to do a small amount of work. So in an amortized setting, you have very low complexity. And the solution is to assume this quantum memory, which you can read in superposition, and you will store your vectors in a binary tree structure, where when you store a vector, you always store the sum or the sum of the absolute value squares of these vectors level above, and in a hierarchical structure, you just store this L2 norm. And this enables you to these efficient algorithms. Yes?
In the previous slide, why do you want to divide by the Frobenius norm? That seems enormous.
Well, this is the best what we can do, and in the case when you have a small major singular values that are the dominant features, and you have not so many of those, and the noise is comparatively small, then this will be the signal to noise ratio. If the signal to noise ratio is not too bad, then this will not kill you. If the signal to noise ratio is bad, then it's bad for you. But I will not talk much about the details of this because Ivan will talk about this much more in the next talk. So we'd like to end up here.
Let's take a few.
Thanks for the talk. I had a question about the circuit diagram for the Coulomb singular value. Might be faster. Go to your laptop.
Should be alright.
It's a ways back. Oh, there it is. Perfect. I just had a question about. So it's the first thing you, then you dagger. What happens in the next one?
Yeah, here it's always you dagger, you dagger, you dagger, just alternating.
And these A's are the blocks that you're trying to pick off, right?
Yeah, if it's a non-symmetric block encoding, so you have A qubits on one side and B on the other side, and you also alternate here. This is A qubits, then it's B qubits, A, B, A, B. So it's an alternating structure.
The whole thing's unitary. You don't do the measurement.
Maybe one more general question. Yes, please.
Do you expect to be able to extend this block encoding to polynomials of non-Hermitian matrices? But then you can't go through the singular value.
Well, you can, since you are able to multiply matrices and take linear combinations, one way is to just do all the monomials individually and then take linear combinations. But there you will pay different costs. This implementation will have cost proportional to the one norm of the coefficients of the polynomial, and that can be bad in some cases. In this case, the one norm of the coefficients doesn't matter. The only thing that matters is the norm of the polynomial in this domain. In the more general case, you might need to pay a higher price.
So there's no issue, because I thought it said you can take convex combinations of matrices, but you're saying you can take linear combinations.
Yeah, it's just I would just simplification. Yeah.
Any other exciting questions? Because we're running late on lunch, I suppose. If not, then let's give Andres a wonderful hand. You should write a book.